Welcome to this explainer. Right out of the gate today, we're unraveling a genuine biological detective story. We're going to track down the exact cellular lock that a highly destructive virus uses to break into its victim's cells. Think of it, like a true crime investigation, but on a microscopic scale. The perpetrator is a tiny pathogen, and the crime scene, well, that's the immune system itself.
Okay, let's dive into this. How does a deadly virus actually choose its victims? Because it doesn't just smash through the cell walls like a wrecking ball. It actually needs a key, a very specific key that fits an exact lock on the cell's surface. Our culprit today is the Infectious Bursal Disease virus, or IBDV for short. Now, for years, scientists knew exactly what this virus did, but the exact molecular lock it used to get inside, that remained a total mystery.
And we really need to understand the stakes here because they are incredibly high. This isn't just some abstract puzzle, it's a massive global agricultural crisis. If IBDV is literally found in over 95% of World Organization for Animal Health member countries, it zeroes in on vulnerable young chickens, mostly between 3 to 6 weeks old. By suppressing their immune systems, it causes devastating mortality rates and just huge economic losses worldwide. We absolutely have to stop it. But you can't build a better security system if you don't even know how the burglar is getting in.
So, here is our microscopic crime scene. You're looking at chicken embryo fibroblast cells showing what we call cytopathic, or basically cell-killing effects, from the IBD virus. Inside the bird, this virus specifically targets lymphoid cells in an organ called the bursa fabricius. It's brutal. It completely depletes the host's B cells by forcing them into apoptosis, which is essentially programmed cell death. It dismantles the entire immune system from the inside out.
Section 1. Hunting the cellular lock.
To stop this microscopic burglar, the investigators needed a prime suspect. So they started looking at the specific cells the virus actually preferred to attack. And the main suspect quickly became a molecule called MHC II, which stands for Major Histocompatibility Complex II. Now, why this specific molecule? Well, researchers noticed that immature B lymphocytes, dendritic cells, and monocytes, basically the exact cells the IBD virus loves to bind to, they all just happen to naturally express this exact MHC II molecule on their surfaces. Coincidence? I mean, in biology there are rarely coincidences, but a suspicion isn't proof, right? They really needed to interrogate this suspect.
So, the researchers set up this brilliant if this, then that interrogation strategy. The logic is just beautifully simple. If MHC II is indeed the lock the virus uses, well then artificially forcing the cells to grow more of these locks on their surface should logically result in way more viruses successfully binding. To test this, they treated the cells with a B-cell activator known as LPS.
And this brilliantly illustrates the results of that exact experiment. Think of this as our surveillance footage. Through immunofluorescent staining, we can literally see the IBDV binding on the lymphocytes. Before the LPS treatment, virus binding sat at around 22.9%. But after using LPS to activate the cells and upregulate those MHC II locks, bam! The binding spiked to over 34%. That is a highly significant increase. Our suspect was looking very, very guilty.
Section 2. Turning the volume dials. To really nail down the identity of the target, the investigators used what we can think of as cellular volume dials, basically specific chemicals used to manipulate the cell's environment. They brought in two agents for this. On the left, we have TGF-beta. This acts as the volume down dial. It actively downregulates or removes MHC II expression on the cell surface. On the right, they used interferon gamma. That's the volume up dial, which does the exact opposite by upregulating and adding a bunch more of those MHC II locks.
Now, what's really interesting about this slide is the incredible precision of the data. When they applied that TGF-beta, turning the cellular volume down and stripping away those MHC second locks, the flow cytometry histograms shifted noticeably. The percentage of lymphocytes that the IBD virus could actually bind to dropped significantly, falling from 21.4% right down to 16.1%. Fewer locks literally equaled fewer break-ins.
And then, when they ran the inverse experiment, using interferon gamma to crank the volume up and add more locks, resulted in both higher MHC expression and, you guessed it, a corresponding increase in the virus binding to the lymphocytes. At this point, the correlation was becoming undeniable. The virus's success was entirely dependent on the presence of this one specific molecule.
Section 3. Blocking the target.
But what happens if you intentionally jam the lock before you even try to check how many locks are there? They ran a really clever competitive blocking experiment.
They took the cells and incubated them with the IBD virus first. The idea was that the virus would find the MHC II locks and attach its key. Then, the scientists came in afterward with a special stain meant to highlight the MHC II locks. But because the virus was already parked in the lock, it essentially hid the MHC II from detection. The percentage of detectable MHC II positive lymphocytes dropped from nearly 21% down to about 18%. The virus and the stain were literally fighting for the exact same parking spot.
Section 4. The T-cell plot twist.
Of course, every great detective story needs a plot twist. Up until now, we've only talked about B cells. In their normal resting state, chicken T cells do not express the MHCI lock. And because they don't have the lock, the IBDV burglar completely ignores them. They aren't even on the virus's radar. This presented the scientists with a totally fascinating opportunity to set a trap.
Here is exactly how they set that trap. Step 1, they activated the T cells using a specific chemical called Con-A. Step 2, they waited. Because when T cells are activated this way, they suddenly begin expressing MHC II locks on their surface. And step 3, they introduced our viral burglar into the environment. The big question was, would the virus break its own rules and attack a T cell just because the lock was suddenly there?
Let's move to the results and see how this builds to the climax of the experiment, because this is just beautiful. The activated T cells successfully grew the MHC II locks, and the absolute second those locks appeared, the virus pounced. It successfully bound to the T cells. It didn't care about the cell type at all. It literally only cared about that molecular lock.
This right here was the smoking gun. As the researchers noted in their report, and I quote, "A simultaneous expression of CD3 and IBDV binding on activated T lymphocytes was observed for the first time. If you give a cell the MHCI lock, the virus is going to use its key to bind to it, completely upending its normal biological behavior."
Section 5. Case closed. So the crucial point is really captured right here in this summary table. With that brilliant T-cell trap sprung, the investigation reached its natural conclusion. Just look at the totality of the evidence. When LPS upregulated the lock, the virus binding increased. When TGF-beta downregulated the lock, binding decreased. When interferon gamma upregulated it again, binding increased again. And finally, when Con-A induced the lock on a cell that usually never has it, it induced virus binding. It is an undeniably consistent link.
The scientific verdict is totally clear. The evidence overwhelmingly proves that the putative molecular target, the exact entry lock for the infectious bursal disease virus on chicken B cells, is, without a doubt, the MHC II molecule. The mystery of the break-in is officially solved.
But, as with all great science, answering one question just opens the door to an even bigger one. If we now know with absolute confidence that MHC II is the universal lock allowing this devastating virus to enter and destroy the immune system, how might we redesign our future immunotherapies? Could we develop treatments that temporarily jam or hide this lock, stopping the virus in its tracks before the infection even begins? It's a hugely thrilling prospect for the future of viral defense. Thank you so much for joining me on this explainer, and keep questioning the science around you.